Hi, I'm Benny D, and in this video we're going to be looking at the language of polynomials. So a polynomial is a function that can be written in the form p of x equals a n x to the n plus a n take 1 x to the n take 1 plus, and we can keep going along all the way up to a1x plus c. Okay, what's that really mean? Okay, what it means is we get polynomials, okay, that look something like this. It could be 3x to the 4 plus 2x cubed plus x squared plus x plus 6. Could be something like that. Okay, so a to the n is this 3, n is the 4, a n take 1 is the 2. This is just saying this is our first coefficient, this is our second. Okay, we keep going up to our last ones, and you see each time here our power's decreasing by 1. That's our convention. Now sometimes you could have something that's got a power of 0 and it just isn't shown there. We're allowed to skip values as well. Okay, so we don't have to have x to the 4, x to the 3, x squared, x, and a constant. Okay, any of those terms could be missing. The number 0 is actually called the zero polynomial. Pretty straightforward. The leading term, a n x to the n, of a polynomial is the term with the highest index and sets the general shape of the graph of p of x. Okay, so we, by convention, always put our highest power first, then work our way down. The degree of a polynomial is the index of that first term. Okay, so e.g. p of x equals x cubed is a polynomial of degree 3, or is a degree 3 polynomial. Okay, so whatever that highest power is at the front, that's the degree of our polynomial. A monic polynomial is a polynomial whose leading coefficient is 1. So our example is p of x equals x squared plus 2x plus 3. Since our coefficient here is 1, okay, we call that a monic polynomial, in this case a monic quadratic. The constant term is the term of index 0, e.g. the term without the x. That's the one at the end. Okay, that's our constant. It doesn't have an x, so it doesn't have a variable. It's constant. It doesn't change. Okay, so it's that number by itself. And lastly, two polynomials, p and q, are only equal if all the corresponding coefficients are equal. And you'll see a little bit about that shortly. So I've got a few worked examples to go through. So, our first one, let p of x equal x cubed take 6x plus 3, and q of x equals x squared take 3x plus 1. Okay, what we want to do is a little bit of arithmetic with our polynomials and find p of x take q of x. Okay, so what we do to find p of x take q of x, okay, is simply, what is p of x? Well, it's x cubed take 6x plus 3. We need to take away q. Now the key here is always put in brackets, okay, otherwise it's really easy to muck up signs. Okay, now what we're going to do is take away our like terms. Okay, so we don't have any, well, we're going to combine like terms, I should say. So we don't have any other x cubed, so we're going to go x cubed. Okay, now it's going to be take x squared. Okay, now we've got 6x take negative 3x, so that's the same as adding 3x, which will give us negative 3x. Okay, 3 take 1 is 2. Okay, so it's as simple as that. For p of x times q of x, a little bit more complicated. Okay, so p of x times q of x. Okay, again, you have to have brackets for these. X cubed take 6x plus 3 times x squared take 3x plus 1. Okay, and we're going to expand those out. So I'm going to need a bit of room for this. So x cubed times x squared, okay, is x to the 5. Okay, x cubed times negative 3x is negative 3x to the 4. X cubed times 1 is x cubed. Okay, negative 6x times x squared will be negative 6x cubed. Negative 6x times negative 3x will be positive 18x squared. Okay, and negative 6x times 1 will be negative 6x. Then we've got positive 3 times x squared will give us 3x squared. Okay, 3 times negative 3x will be negative 9x. And 3 times 1 is 3. And we can combine like terms here. So I've only got one term with a power of 5, so that'll be x to the 5. Okay, take 3x to the 4. Now I've got x cubed, take 6x cubed. Okay, gives us negative 5x cubed. Okay, 18x squared plus 3x squared will give us 21x squared. Okay, negative 6x take 9x will give us negative 15x. And then we've got that constant value there of 3. Okay, so it's just a matter of expanding some brackets there. And our second worked example, a polynomial p of x equals x cubed plus 3x squared plus 2x plus 1 can be written in the form p of x equals x take 2 times x squared plus bx plus c. We need to find the values of b and c. Now there's two different ways that we could go about this question. Since we know that x take 2 is a factor of this, what we could do is divide p of x by x take 2 through division of polynomials. That would leave us with this x squared plus bx plus c, and we could simply equate our coefficients. Okay, but we're going to go the other way on this, and we're actually going to expand this out. Okay, so it's in this form, and then equate our coefficients. So I'm going to go x times x squared gives us x cubed. Okay, plus we're going to get bx squared plus cx. Then we're going to get take 2x squared, take 2bx, take 2c. Okay, what we need to do is actually just rearrange this a little bit so we get our like terms next to each other. Okay, so we're going to get plus bx squared take 2x squared plus cx take 2bx take 2c. Okay, now what I'm going to do here with these like terms, so I'm going to take x squared out as a common factor. So we've got x cubed plus b take 2x squared. Okay, same thing here. I'm going to go plus c take 2b x take 2c. Okay, and then what we can do here is now go through and equate our coefficients. So I can see that I've got b take 2, that's our coefficient of x squared, equals 3 up here. So b has to equal 5. So then when I equate my coefficients here, I've got c take 2b equals 2. But I know b equals 5, so I've got c take 2 times 5 is 10 equals 2. So c equals 12. Okay, so I've got those values of b and c. Now in our last worked example, a little bit different. We want to show that x cubed plus 6x squared plus 6x plus 8 cannot be written in the form a outside of x plus c cubed plus b. Now our strategy here is we're going to actually expand this first and look at equating denominators to see what actually happens here. Okay, so when I expand this, I'm going to leave this a out the front. So I've got x plus c, x plus c, x plus c plus b. So I'm going to say I've got x squared plus 2 times x times c, 2xc or cx, I should write 2cx, okay, plus c squared. Then I've got to times that by x plus c plus b. So I've got a times, I'm going to get x, I'm going to get x cubed, okay, plus cx squared. Then I'm going to get plus 2cx squared plus 2c squared x plus c squared x plus c cubed, okay, plus b. I need to collect like terms, and I'll multiply out by this a as well. So I've only got one term that's x cubed, so I'm going to get ax cubed. Now I've got cx squared plus 2cx squared gives me 3cx squared. Okay, times my a is 3acx squared. Okay, then again I've got 3 of these, so I'm going to get plus 3ac squared x plus ac cubed plus b. Okay, so what we're going to do is go through and have a look at our coefficients here. So here I've got ax cubed, and comparing that to x cubed, well, that tells me that a has to equal 1. Okay, so I keep working along here. Okay, if here I'm saying 3 times a, which is 1, so just 3 times c, okay, has to equal 6. So c has to equal 2. When I look here, I have 3 times 1, which is just 3 times c squared, so times 2 squared, which is 4, okay, has to equal 6. Well, hang on, I've got 12 equaling 6. That's not true. Okay, and we can actually finish here and say, because we've got this, okay, which is not true, you can't say that 12 equals 6. Okay, we've shown that this can't be expressed in that form. Okay, if we kept on going through, okay, we'd see we'd still have problems here. Like we've got problems there. We'd also probably find that we've got problems with this constant term equaling 8 as well. Okay, so there's a few worked examples that'll hopefully help you through on the questions for this section.